All right, let's get right into it. Today, we are taking a deep dive into the massive machines that power pretty much everything in our modern world. We're going to trace the journey of energy, all the way from a piece of fuel to the electricity that's lighting up your screen right now, by exploring how a thermal power plant actually works.
I mean, really think about it. How does this simple, black rock get turned into the bright lights of a city skyline? It feels like it should be magic, right? Well, it's not magic. It's an absolutely fascinating process of physics and engineering, and we're going to break down every single step.
And to guide us on this journey, we're not just reading from a textbook. We're drawing on the know-how of Amir Ranjan Malik, an engineer who spent more than 2 decades working inside these very plants. So, this is the real deal. Knowledge coming straight from the heart of the machine.
So, our journey has to start with the raw material, coal. But it's not as simple as just, throwing it into a furnace. The very first step, and honestly, one of the most critical, is getting that fuel ready to release its energy in the most efficient way possible.
Before it can ever create heat, the coal gets a 3-step makeover. First, it gets unloaded and stored. Then, massive crushers get to work, breaking down big chunks. But the real game changer is that last step, pulverizing. The coal is ground down into a powder that's as fine as flour. So why do that? It's all about maximizing surface area. This way, when it's blown into the boiler, it ignites almost instantly and burns completely, releasing a colossal amount of heat in a very, very controlled way.
So how do engineers know if the coal they're getting is tough and stubborn or something a bit softer? That's where something called the Hard-Grove Grindability Index, or HGI, comes in. Basically, a higher HGI means the coal is easier to grind up. And this one number? It's absolutely crucial. It tells the engineers exactly which type of pulverizer to use and how much energy it's going to take. If you get it right, the plant runs like a dream. Get it wrong, and you're just wasting energy and money before you've even lit the fire.
Okay, so we've got our powdered fuel ready to go. Now we're heading to the absolute heart of the plant, the boiler. And look, this is not your kitchen kettle. We are talking about a gigantic structure, sometimes as tall as a skyscraper, where all that chemical energy locked inside the coal is about to be unleashed as pure, intense heat. So as that powdered coal ignites, it creates this huge fireball with temperatures just soaring. The walls of this furnace are lined with thousands and thousands of tubes, all filled with water. So the big challenge here is, how do you get all of that incredible heat from the fire into that water as fast and efficiently as humanly possible?
And what's so cool is how basic physics just takes over inside that boiler. You've got 3 different types of heat transfer all working together at once. First, the fireball radiates heat, just like a campfire warms your hands, even from a distance. Second, hot gases swirl all around the tubes in a process we call convection. And finally, that heat conducts right through the metal of the tubes into the water, just like that spoon heating up in your tea. It's a perfectly orchestrated symphony of heat.
And all of this is happening under just unbelievable pressure. In a modern supercritical boiler, we're talking pressures that can top 225 kilograms per square centimeter. To put that in perspective, that's more than 220 times the normal air pressure that's all around us right now. This insane pressure is the secret to creating incredibly efficient, superheated steam. So we've made this incredibly high-pressure, superheated steam. Now what do we do with it? Well, now it's time to unleash its power and turn all of that heat energy into raw physical motion. This is where the real action happens. That high-pressure steam is shot through nozzles and blasted onto hundreds of turbine blades, which are all shaped like tiny, complex airplane wings. You can think of it like a whole series of super sophisticated pinwheels, all attached to one single shaft. The pure force of the steam hitting those blades spins the entire rotor at mind-boggling speeds. We're talking 3,000 revolutions per minute. Okay, so we've done it. We've converted heat into incredible rotational speed. That turbine shaft is just spinning like crazy. Now for the final step, turning that motion into the one thing we're all here for, electricity. That spinning turbine is connected directly to a generator, and in the simplest terms, a generator is just a massive magnet spinning inside a giant coil of copper wire. As that magnetic field sweeps past the wire, it literally pushes the electrons in the copper, and that creates an electric current. That's it. That's electromagnetic induction, the principle that generates pretty much all the electricity we use in the world. Generating this much power creates a ridiculous amount of heat. Now, smaller generators can just be cooled with air, no problem. But the big ones, the ones in these massive plants, they need something way more effective. And that something is hydrogen gas. See, hydrogen is so much less dense and transfers heat so much better than air that it can cool the generator way more efficiently. This allows it to produce a lot more power without melting down.
But wait, the journey isn't quite over. A power plant isn't just a one-way street. It's a continuous, closed-loop cycle. And to keep that cycle running safely, efficiently, and cleanly, there are a whole bunch of critical support systems working behind the scenes 24/7.
You definitely can't just pump regular tap water into those high-pressure boiler tubes. You know the hard white scale that builds up in your kettle at home? Now imagine that happening inside pipes that are under immense pressure. It would be a total disaster. And that's exactly why the water goes through this high-tech purification process first. It's basically a series of chemical filters that grab and remove all the dissolved minerals, making sure the water is ultra-pure before it ever sees the boiler.
So what happens to all the smoke and ash after the coal is burned? Well, the exhaust gas is filled with these tiny particles called fly ash, and just letting that go up the chimney would be a huge environmental problem. This is where a really clever piece of tech comes in, the electrostatic precipitator, or ESP. Think of it as a giant static electricity magnet. As the exhaust gas flows through it, the ESP zaps all the little ash particles with a negative charge. Then they float past these huge metal plates that have a positive charge. And you know what happens next, right? Just like a sock sticking to a blanket out of the dryer, the ash particles get pulled out of the air and stick to the plates. This system is so good it can remove over 99% of them. And the collected ash doesn't even go to waste. It's often reused in things like concrete, turning a pollutant into a valuable product. So from grinding coal to purifying water and generating a current, it's just an incredible process. But engineers are always pushing the limits. The next generation of these plants, they're called advanced ultra supercritical, are designed to run at even hotter temperatures, over 700 degrees Celsius, all to squeeze every last drop of efficiency out of the fuel. It really makes you wonder what kind of breakthroughs will be powering our future.